Okay, last week we cover text classification 1, but we discussed about the unsupervised learning, which cover the clustering. So for the clustering, we have two parts. The first one is the partitional clustering. The second one deals with the hierarchical agglomerative clustering. And we also cover the naive text classification that use distance method in order to measure the distance between the unseen document to the class label. So that is similar to finding the distance between the query and also the document. Today, we will cover the text classification part 2, but we cover the supervised learning, in which we have labels as a guidance for us to train our model. For the supervised learning, we need to have training set that has label. So each of the document will have labels, and each of the document will be represented by words or term that's selected prior to the modeling. So our task is to find a model or train a model for the label of the document as a function of the content of the document. So which means that we need to find a model that will map the document to the class label. So we need to find this function, meaning that we need to train the model whichever machine learning method that we have. So the goal is, when we find this model, when we have a new unseen document, so we should be able to assign the right class for the new unseen document. So normally what we do is that we will train the model. We will train this model using the training dataset. And we also, once we get this model, we will train them, we will test them using the test dataset. So we will have two dataset. One is to for training the model, and the other one is to perform the test. The test is used to assess the performance of the model in terms of accuracy. How many percentage of the document is classified correctly? So this refers to the accuracy. So if you look at the diagram here, for the classification task, we always divide our data into training and test dataset. So normally they will divide them into 70% for the training and 30% for the testing. Or we could have 80% and this is 20. Some may have used 90% and 10% for the testing. So it depends on the characteristic of the dataset. We may have different percentage of partition in order to optimize the performance of the model. Once we split them into training and test dataset, then we use the label document in order to train this model. So the learning algorithm could be decision tree or SVM or naive Bayes. So we have so many methods that can be used for classification. So our task is classification, in which we classify document into the classes. Once we have learned the model, or once we have trained the model, then we use that particular model and then we use the label document for the test set to predict the class of this label document. And from here, we assess how many documents that are correctly classified. Because we have the label already, so we compare the actual labels with the predicted label produced by the model. So that's how we compute the accuracy of the classification. So to define the supervised algorithm, it depends on a training set. So we should have a subset of training document. So which means that we have set of training set, which part of the full document. So we need to find a function, a training set function that will map this document to the class that we have. So either the document belong to the class or not. So the idea is we want to assign to each pair of this. So we have one document and also the class. We want to map the document to the class label, where the document belong to the set of training document, and this class belong to the full set of the class that we have. So if they belong to the class, that means the value is 1, otherwise 0. So we will compare how many 1 and how many 0 that we have. So we are comparing between the actual class versus the predicted class that we have. So this function that we have, we can train them by modifying what is the input that we feed into the model. So we fine tune the classifier depending on what parameter we have for individual classifier that we have. So that's why when you want to perform classification for using a specific classification method, we need to know what are the parameters that can be adjusted in order to optimize the performance of the classifier. So during the training phase of the classifier, so given this is the class level that we have 3 classes. So this is the set of document, and then this is the U. Okay. So what happens is that we will see how many belong to class 1, class 2, and class 3. Okay. And then we will use this document to train the classifier here. Okay. So to evaluate the classifier, we use a test set. So this is the second part of our data set. So a subset of document with no intersection with the training set. So that means we have no overlapping. So the classes to document will be determined by the human specialist. So this is you. Okay, so we have the training, we have the testing document, we have the classes. So we assign the label to the document. Okay, so when we finish with a 2-step process, so we use the classifier to assign the classes to document in the test set. So we compare classes assigned by classifier with those specified by human specialist. So this is your actual class here. This is your predicted class here. So we comparing. So we measure how many percentage of the document is correctly classified by the model. So we can try a few type of classifiers because each classifier may have different parameter that you can adjust. So when it goes to the actual classification and evaluation, so this is your document test set. Okay, so we change into vector, and then we select the word, and then once we select the word for individual document that we have, then we use that particular text in order to classify them. So based on the class assigned to them, so this is the predicted class. This is the actual class from the test set. So we will compare how many percentage of the document that are correctly classified. So once we have trained and validate, so basically when we train and validate means we have test them or validate them that we have the best classifier for that particular data set. So once we have trained and validate them, so we can use them to classify new and unseen documents. So when we have new document, so we can apply the classifier in order to classify this new and unseen document. If the classifier is well tuned, your classification percentage will be very, very high. Otherwise, you may have to fine tune your classifier. So that is the difficult part about classifier. So we will look into this in the next semester, where we learn about more about machine learning. But I know you have studied data mining and warehouse. You may have some idea on how we can use the classifier to classify the text document. So today what we will cover these two, which is the decision tree classifier and also k nearest neighbor classifier. So this is considered as lazy model because we do not have to model them. We do not have to train our model because we use the distance method in order to determine the class label for the unseen document. But for this decision tree, we need to train them. Okay, we need to feed the training data set. We need to test the performance of the model using the test data set. Then we can deploy them. So first, now let's take a look at the decision tree. So for the decision tree, training set is used to build the classification rules. So your decision tree will look like this. So depending on the word that you have, so maybe here this is sports, maybe this is politics and so on. So at the root here, they will look at word that exists in your document. So for example, this is science. So this is the word. And then we have technology here. So this is at this particular node. So we use the word to split the document. And finally, when we reach here at the leaf of the tree is the class label. Okay? So this is the basic procedure for the classification, but the issue that we want to look into here is what is the best word that we can use to split the data in order to reach to the final class label. So the decision tree is organized as path in tree. So for example, if you want to reach at this class label, you need to have the science, technology, and so on. And the three paths used to classify documents, so which means that for us to classify them as a politic, book, or document, so we have to use this path. This is also called rules, where you can say if the document have science, technology, and something here, maybe politics. So we are talking about political science. So this is how it looks like. And how do we actually construct the tree? So that is the main issue here. So how do we actually pick what is the best term or value that we can use to split the tree, so that at the end here we will have all with the same label. Okay. So for example, like this, we have the training data set here. So when we say training the data set, we need to construct the model so that when we have the new test here, the new test instance, we would be able to determine whether we want to play or not. So the decision is to play or not. Play
Excuse me,
or
doctor.
yes.
Sorry, doctor, but some of the students are still in the lobby. They are waiting to enter the class.
Okay, let me say one of them. Okay, so they are in already. Okay, can you see the slide again?
Yes.
Yes, doctor.
Okay, so when we given this data set, so this is your label. Okay, the label means the decision to play or not depending on the outlook, the temperature, humidity, and windy. So when we are given this test instant, so our task is to find this value, yes or no. Are we going to play or not play? Okay. So this is the structure that we are going to have, or the input that we are going to have. So how actually we build the tree? Okay. So when we provided with this training data set, our task is to build this model. Behind the scene, what happened? What happened when you train the data set? So remember that we have a training data set. We will train the model, and then once we model the data, then we use the test data set in order to validate the model or assess the performance of the model. So this is the example of the decision tree. So they say that if our outlook is sunny, I go here. If rainy, I go here. If overcast, I go here. Okay. So at the end of the tree, this is the leaf of the tree. This is the label. So for us to go here, which means that we don't play if the outlook is rainy and windy. So we don't play. So if the outlook is sunny and humidity is normal, then we play. So this is the structure of our decision tree after we perform the training. So our question is, how do we actually construct the tree? How do we know that, okay, the first one, we will look at the attribute of the outlook. So remember that we have 1, 2, 3, 4. We have 4 features, right? So how do we know that, okay, I will go for this first to be my first node? Why didn't I pick temperature? Why didn't I pick humidity and windy? So there is a way on how we can determine which one is the best one. Which one is the best feature for us to use to split our data. Okay. So when we convert them into rules, so basically what we have in the internal node is the name of the attribute, and then the edges will be the value for that individual attribute that we have, and the last one will be your class label. Okay, so whatever value we have here, we just map them into the model. Then we can find this, the answer for this. Okay, so this is your rules saying that if the outlook is sunny and humidity is high, then we say no. So this is based on the value here and here. So the answer here is no. So this is more on the application of the classifier on how do we classify test instance based on the value of their own attribute. Okay. So the basic technique is to perform the prediction based on scene instance. So scene instance means you have the trained data set. So you train the model. So the new instance that violate scene pattern will lead to error. Okay, so which means that you will have misclassified item, although they match all the rules, but they are classified into the wrong classes. So these are the things that we want to fix. Okay. So the issue that we want to address here is the splitting process. We want to know which attribute is the best one. So for example, in our data at the moment, we have 4 attributes. So the 3 that's shown just now show that we use the outlook attribute as the first node in our decision tree. Okay. So when we want to determine the splitting process, the first thing that we need to do is we want to select one of the attribute other than the play, because this is your label. We cannot take this one as your root. We must select from the other attributes. And then we use the attribute values to split the tuples or the record into subset of document that we have. So for each of the subset of tuples, we select again the second splitting attribute until we reach where all the document in the particular partition all belong to the same classes. So for example, like this is the step-by-step splitting process. So when we split the data into here, so we have this is the record ID, and then we split again using humidity, and then we split again for using the windy, and then finally we have this. Okay. So we normally stop when we see all the member in this particular partition belong to one class only. Or maybe we can say that, okay, the depth is only two depth of 2, or all the member belong to the same class. Okay. And you may have unbalanced tree. I know that you study in data structure, you study about balanced tree. How do you balance the tree? By shifting to the right, to the left, and so on, if you still remember. Okay, so we need to have a balanced tree. Okay, we do not want to have two the weight to the left or to the right. So what we want to have is a balance or near balanced tree are more efficient for predicting attribute. Can you guess why we need to have this balanced tree? Because the deeper you go, the more computation that you will need. the time to compute, the time to compare. Okay, so we need to have a balance or near balanced tree. So rule of the thumb is select attribute that reduce average path of the length. So that means we go one by one. And then, for example, like this, then you split them level by level. You don't go one area and then you expand. So this one make your tree unbalanced. Okay. So for document classification, how do we apply the tree? How do we visualize the application of the tree for document classification? So what we have here is that they say, okay, for each of the node, we will have index term. And then with each leaf associated with the document class. So with the age associated binary predicates that indicate the present or absent of the index term. So whether they exist or not exist. So if we formalize the classification for the document, so we will have a set of nodes, V, and then we will have a tree consisting of the nodes, the edges, and also the root. Okay, so this is an acyclic graph on V, which means that we will not have a cyclic or a circle inside our graph. So this one say, okay, the edges is a subset of the vertex that connect to another vertex. So we have, this is our root and also called V and connect to another V. So this is your edges. Okay. So, and they said let edge V1 Vj. So they're assuming that, okay, in general, we have Vi and Vj belong to the edges that we have. And V1, Vi is the father and Vj is the children. And then the R is belong to the root. So this is belong to the, no, the root is belong to the vertex, is part of the vertex. And the I set of all internal nodes. So this is set of all the internal nodes, which is this one. And then the complement of I is set of all the leaves. So we will have this connect to another vertex. So this is leaf. Okay, so this is your I. So this is how we formalize the classification of the document. So for example, this is your root, and then if they belong to chemistry, you go here, and then atom, you go here, and science, and so on. And so we split them into two. So when we apply in the real world for the classification, okay, so we basically take this, we take the keyword here. Okay, so we have a list of keyword here, K1 up to KT, and we also have the predefined set of all classes, and we have set of logical predicates of the index, whether they exist or not. Okay. So the decision tree consists of the vertex, the edge, the root, the internal function. This is a function that associates with each internal node of the tree, one or more index, and also we have a function that map to the non-internal, which refer to the class label that we have. So this is your class, this is your internal node, and this is the internal edge that that associate with each edge of the tree a logical predicate from P. So a logical predicate refer to whether the wood exists or not in your document. Okay? So if we look at the step, so the first thing that we need to do is we need to associate all document with the root. So they start from the root. And then the second step is the select index term that provide a good separation of the document. Okay, so that means if we have 1,000 word, then we need to pick one word that can split our document into two, that will minimize the percentage of different classes here. So we want to minimize, or I would say maximize the percentage of same class label. And then we will repeat again, splitting until we find all the member belong to the same class here. Okay. So for example, like this. So if this is your root, so if your document has keyword A or B or C, they goes to different path. And then you split again. If they have the keyword D and then E, they will go to separate partition. And we also have F and G. Okay. So finally we have this. So for this one, once we have stopped, so we assume that, okay, this one belong to class D, class B, class C, class E, and class A, and class F. So all the leaf are considered as leaf. Okay. So again, we go back to the, how do we select the best wood, or how do we select the best term? So we will use the same benchmarking that we used before. So you came across this information gain and entropy previously. So what happened in the entropy is that once we have all the document belong to the same class, so the entropy will be 0. Okay. So if your leaf contain like 1, 2, 3. Okay, so we have 3 belong to class 1, 3 belong to class 2, so the entropy would be 1. Okay. Okay, so we will use this entropy. So the selection of term with high information gain tend to increase number of branches at a given level. So reduce number of document in each resulting subset. Of course, when you split, you will have less number of document, and it also yields smaller and less complex decision tree. Okay, so that's the good thing about information gain. So how do we apply this? So you remember this formula. So the entropy can be defined as the summation of all the probability of that document belong to this class times log base 2 times the probability of the document given the class that we have. Okay. So how do we apply this formula? So for example, if this is your leaf, so the probability of having class 1 is 0. The probability of having class 2 is 1. So when we add up the value here, because this is the summation, so we look at the summation of first when we have the class 1, this is your class 1, and this is your class 2. So since we have all the document belong to class 2 and none from class 1, so your value will be 0. So entropy is 0. So we can use this indication to show how pure is your partition when you split the document into 2, depending on the word that you use to split them. Okay, and again, this is another example, but this is 1/6 and 5/6. Okay, so this is for the class 1, this is for the class 2. So we compute, we have this. Okay, and again, if we have 2, so we have class 1, the probability is 2/6, class 2, 4/6. So we will have this value for the class 1 and this value for the class 2. When you compute, we have this. So eventually, if we have 3 here, your value here will become 1. So based on this, we can say that we will have a good partition if the value is 0, if the entropy is 0. Okay, so this is only the entropy, but the information gain is computed based on before and after. So this is before splitting. What is the entropy? This is after splitting. Okay, so if your entropy, the initial entropy is high, and then once you split, you can reduce the entropy. So the gain here will be maximized, right? So if this is high, this is low, then you have maximum gain. But if this is high and after splitting, you also have high, so high minus high, you get a small number here. Okay, so let's take a look at how do we compute the IG. We know already how to compute the entropy. So for example, like this, this is before splitting. We have 18 document consisting 15 class 1 and 3 class 2. But if we use the keyword to split them, and we have this partition. Okay, so this part here is before. So we need to compute what is the entropy before. And this part is after. So we need to compute what is the entropy after we split. Okay. So for before splitting them, so we know that we have 15 and 3. So we just plug in the value. This is for class 1. And this is for class 2. And then we compute, then we get 0.65. Okay. And for once we use the keyword A, B, C, then we split them into 3 partitions. So we compute the individual entropy for each of the partition. We have this and this, but we need to use the weightage for each one of them. So the first one is 6/18. So this is what we call the weightage. If we look at the formula here, so this is the weightage. Okay. So we have 6/18, and then over here we have 6/18 also, and over here we have 6/18. So this comprises of all the total entropy after we split, which turned out to be 0.53. And the information gain will be 0.12. So what we want to do is we want to reduce this so that we can maximize this value. We cannot change anything about this one because this is the initial entropy. So what we can do is we find the right keyword to split them. Okay, this is for A, B, C. Okay, let's suppose I have a keyword C, D, F. And now my partition will be different. Okay, so this one, based on the formula, we know that, okay, the entropy is 0. And for this one is 0.92. Is it 0.92? I think it's 0.1. Okay, let's compute again. Let's try this one. So what is the entropy? So that is 0.5 log 2, 0.5 times 2. I just double check because we have, oh yeah. So this is 3/6. Betul lah. So let me double check with the ini. Supposed to be 1/3. Okay. So I go back to the slide. So this is, okay, how do we get that? It's basically this value. I put bottom here. So this is the entropy for the first one when we have C. Okay. So how do we get this one is because we have 3 and 6. So that means 1/3 because 3/9 and the other one is 2/3. Okay. So that's how we get this. So when we plug in, so this is the weightage 9/18. This is 5/18, 4/18, depending on the total here. This is 0. Then we get this. Then so the information gain here is 0.19. So we can tell that by using CDF, we have higher information gain, which means we better use the keyword CDF instead of ABC. Yes. Okay. So that's how we determine what keyword should we use to split them and how many of them. So we use information gain. The higher is the information gain, the better is the keyword perform in terms of partitioning them. Okay. So this is your task. I'll just leave it for you to do it. So basically we have 20 here, 10 for class 1 and 10 for class 2. And we have X, Y, Z. And then we just compute individual entropy and then we just plug in. Okay. So the problem with this is that because we are building the tree based on keyword. So what if the document do not have the keyword? Okay, so that is the problem. So the solution is we delay the finalized process of the tree construction until all the document is, or we can include the document, the new document presented for the modeling. So which means that we make sure that the document that we have can be classified, which means that they consist word that can reach at the end or to the leaf of the tree. Okay, another solution is to build tree based on feature presented in this document, avoiding the problem. So that means we make sure that the document that we want to classify consists all the basic term that we have in our decision tree model. Okay. Any question? You will learn more about this in the next semester where we learn machine learning, but we learn more. We learn more models. We will learn more technique on how to improve them. So this is just to introduce to you how do we perform supervised learning to classify them. Okay. Okay, for the second part, this is called the KNN, also known as K nearest neighbor classifier. So for this one, based on the name of the classifier, K nearest neighbor means we assign the class based on the distance between the K nearest neighbor. K refer to K number of nearest neighbor. So K could be 3 or 4 and so on. Okay. So this is lazy classifier because we don't have to model. We don't have to go through the training phase. So what we need to do is we need to just find the distance of the K nearest document that we have, and we assign the label, the majority label that we have for the nearest neighbor that we have. Okay, so lazy classifier do not build a model, means we don't go through the training process. The classification done when the new document is presented based on the majority class of the K nearest neighbor that we have for that particular document. Okay, so we use the class of this neighbor to determine the class of the new document. Okay, so our task is to find which document or which K document that is nearest to that particular document. So again, we use the cosine function. Okay, so for example, like this document DJ, should it be belong to class A or class B, but majority of them coming from this class B. So we assign the class for this as class B. Okay. So what we want to know about the KNN is what distance method will be used in order to compute. So our task is to each document class P, we assign a score, which is the distance between the this document to the other document that we have. So for example, over here, we are looking the similarity between the document here and also the nearest document. And then we will take the majority of the class of the nearest neighbor to be assigned to the document here. Okay? So this one refer to set of k nearest neighbor of that particular document. And we use the cosine formula to compute the distance. And we will assign the class label to the document depending on the majority of the class label from the nearest neighbor that we have. Okay. Okay. So this is a simple exercise. So given document 1 and the similarity distance table as shown above. So we have 339 document here. This is document ID. This is the distance. So if I take, okay, I want to classify using 1 and n. So that means we just pick this one only, A. If 2 and n means I have 2 nearest neighbors, so it could be A or B. So maybe we can, by default, pick the first one. Okay. So if we pick 3 and n, so we have this majority is B, we assign B. Okay, so if we pick 4, again equal, so we may say, okay, I'll take the nearest one. Similar to 5 and n, and then if I take 6 and n, then the majority will be A. So I will assign A. Okay. And the issue here again is what is the best K? So for all the data set you have, then you may need to run 1 up to 10 nearest neighbor, and we take the average, which K value produce the best percentage. So we need to have a few experiment, maybe splitting the data into 70, 30, but we do not have the training. So what happens is that we will have different data set, different set of data set for us to measure. Okay. Okay. So like I mentioned just now, what is the best value of K? And also we have to compute distance. So this is very time consuming. For example, if we have 1 million document, so that means we need to compute the distance between the new document to the 1 million document that we have, only to find 3 nearest neighbor. So high competition. And also we need to determine what is the best K. And of course, in research, that's what we do. We investigate what is the best K, and then we reduce the computation time by using parallel programming or quantum machine learning in order to improve the computation time. Okay, so that's all for this session number 9. Text classification using supervised learning. Any question?
No questions, doctor.
Okay. Let me share the